The night sky is a precise, navigable coordinate system projected onto the celestial sphere. Astronomers have divided this map into 88 officially recognized constellations, serving as the fundamental grid for every observation. To master this map, we use a technique called star hopping, anchoring ourselves to bright beacons. In the early months of 2026, the Northern Hemisphere is dominated by a massive asterism acting as the ultimate guidepost, the Winter Hexagon. This geometric pattern links 6 first-magnitude stars around the constellation of Orion. It begins at Rigel, the blue-white supergiant marking the Hunter's Foot, a star tens of thousands of times more luminous than our Sun. From Rigel, we trace the perimeter clockwise to find Aldebaran, the fiery eye of Taurus. As an evolved K-type giant, Aldebaran glows with a distinct orange hue that contrasts sharply with the hot blues of Orion. Continuing northward, we reach Capella in Auriga, a complex system appearing as a single golden point. Sitting just 43 light-years away, Capella commands the northern vertex of the hexagon with piercing intensity. Moving down the eastern side, we encounter Pollux in Gemini. While its twin Castor is a complex system, Pollux stands out as an orange giant, serving as a reliable marker for planetary transits near the ecliptic. Below Gemini lies Procyon in Canis Minor. While a standard main sequence star, its proximity makes it the 8th brightest star in the heavens, bridging the gap to the hexagon's southern tip. The circuit completes at Sirius in Canis Major, the brightest star in the night sky. With a visual magnitude of -1.46, Sirius blazes with white light, often scintillating with prismatic colors near the horizon. Understanding Sirius requires the magnitude scale, where lower numbers indicate higher brilliance. A magnitude 1 star is exactly 100 times brighter than a magnitude 6 star, which is the limit of human vision. Objects like Venus or Jupiter often dip into negative magnitudes, shining far brighter than any star. This logarithmic scale allows us to calibrate our expectations before we ever put an eye to the eyepiece. To apply this, return to Orion, the central anchor of the winter sky. Locate the 3 distinct stars of Orion's belt, Alnitak, Alnilam, and Mintaka, which form a perfect cosmic pointer. Drawing a line downward and to the left through the belt inevitably strikes Sirius. This precise alignment has been used by navigators for millennia to orient themselves when the horizon is obscured. Conversely, drawing that line upward leads directly back to Aldebaran. Continuing the trajectory past the red giant creates a collision course with the dense knot of blue-white stars known as the Pleiades. The Pleiades is an open cluster containing over 1,000 infant stars. Seeing this microscopic dipper clearly is a standard test for visual acuity, proving your eyes have shifted into night vision mode. Mastering the winter hexagon provides a rigid framework for the 2026 observing season. Once you identify these 6 pillars and use Orion's belt as a vector, you can navigate the entire winter sky with confidence. With the map established, the stage is set for the dynamic events that will traverse this backdrop. Now that you can navigate the static stars, let's examine the rare phenomena passing through this region. The static constellations provide our map, but the solar system provides the drama. 2026 is defined by dynamic, high-energy alignment events. We are looking at a calendar packed with oppositions, syzygies, and eclipses that demand precise timing to witness. The year opens with a significant lunar event on January 3rd, the Wolf Moon Supermoon. This describes a specific orbital configuration known as perigee syzygy, where the moon is closest to Earth while simultaneously aligned opposite the sun. Because of this proximity, this full moon appears 14% larger and 30% brighter than a micromoon at apogee.
This increased luminosity washes out fainter stars, making deep sky observation difficult, but offers an unparalleled opportunity for high-contrast lunar surface photography. Just 1 week later, on January 10th, the solar system shifts focus to its largest architect. Jupiter reaches opposition, a point in its orbit where Earth sits directly between the gas giant and the Sun. This alignment means Jupiter rises exactly at sunset and remains visible all night. At opposition, the distance between our worlds is minimized, making Jupiter appear brighter than at any other time in its 13-month synodic cycle. The planet is fully illuminated, revealing the intricate turbulence of its cloud bands and the churning anticyclonic storm of the Great Red Spot.
In February, the orbital dance produces a shadow play. On February 17th, an annular solar eclipse occurs, though its path of untumbra is restricted primarily to Antarctica. While geometrically fascinating, this ring of fire serves as a prelude to the spectacles later in the year. On March 3rd, the geometry aligns for a total lunar eclipse, visible across North America and Asia. During this event, Earth passes precisely between the Sun and the Moon, casting its umbral shadow across the lunar surface. The Moon will not disappear, but will darken into a deep copper-red hue. This blood moon phenomenon is caused by Rayleigh scattering, the same physics that makes our sky blue. Earth's atmosphere filters out shorter blue wavelengths of sunlight while bending longer red wavelengths into the shadow cone, effectively projecting all of Earth's sunrises and sunsets onto the Moon simultaneously. The crown jewel of the calendar arrives on August 12th. A total solar eclipse will sweep across the northern hemisphere, cutting a path of totality through Greenland, Iceland, and northern Spain. Unlike an annular eclipse, the Moon's apparent diameter will be sufficient to completely cover the solar disk. For observers within the narrow band of totality, the photosphere will vanish, revealing the ethereal white filaments of the solar corona, the Sun's superheated outer atmosphere. This is the only time the corona is visible to the naked eye, appearing as a halo of plasma reaching temperatures of millions of degrees. As the year closes, planetary dynamics offer one final display in November. Mars and Jupiter will approach a tight conjunction, appearing in the pre-dawn sky so close together that they will fit within a single field of view of standard binoculars. This is a line-of-sight illusion, but a stunning one. These events, supermoons, oppositions, and eclipses, are strictly governed by celestial mechanics, meaning if you miss the window, the opportunity is gone. To truly appreciate these phenomena, you need more than just a calendar. You need the capacity to resolve the details. This brings us to the critical question of hardware. Seeing the Great Red Spot or the distinct phases of an eclipse requires specific optical capabilities. Whether you are using the naked eye, binoculars, or a telescope, the quality of your observation depends entirely on aperture and magnification. Let us now analyze the current equipment landscape to determine exactly which instruments will give you the best seat in the house for this cosmic performance. Observing the cosmos is ultimately an exercise in capturing photons that have traveled across the void for millions of years. To do this effectively, we must strip away the marketing hype surrounding magnification power and focus on the single most critical metric in optical engineering: aperture. Aperture is simply the diameter of your telescope's primary lens or mirror, dictating exactly how much light the instrument can gather. In the physics of optics, a larger aperture does not just make objects bigger, it resolves finer details and reveals objects mathematically too faint for smaller instruments. For the 2026 hardware landscape, we establish a strict baseline for any serious observer moving beyond toy-grade equipment. You should seek a minimum aperture of 70 millimeters for refractor telescopes, or 114 millimeters if you're choosing a reflector design. Below these thresholds, optical resolution is insufficient to clearly resolve planetary features like the cloud bands of Jupiter. Once you've secured sufficient aperture, the next priority is stability, which brings us to the critical debate between mount types. We strongly advise beginners to avoid cheap equatorial mounts, which are notoriously complex to align and prone to frustrating wobbles. Instead, prioritize an alt-azimuth or Dobsonian mount, which offers a robust point-and-shoot architecture that maximizes your time observing rather than wrestling with gear mechanics. For the purist seeking the highest raw performance per dollar, the light bucket design remains the gold standard. The Apertura AD8 Dobsonian is a prime example, offering a massive 8-inch mirror that acts as a photon funnel, capable of revealing the spiral structure of faint galaxies. However, the greatest challenge for any newcomer is not seeing the object, but locating it in the vastness of the celestial sphere. This is where the 2025 technology market has shifted, integrating smartphone processing power directly into the optical system to solve the navigation problem. Systems like the Celestron StarSense Explorer utilize plate-solving technology, where your phone's camera analyzes the star field in real time. The application generates precise directional arrows on your screen, guiding you manually to your target with an accuracy once reserved for expensive computerized mounts. If manual tracking feels archaic, we are witnessing the rise of fully robotic smart telescopes like the ZWO Seestar S50. These all-in-one units abandon the eyepiece entirely, using built-in sensors to capture and stack long-exposure images automatically, transmitting the result directly to your mobile device. This technology is particularly revolutionary for urban observers, as the digital processing filters out city light pollution to reveal deep sky nebulae invisible to the naked eye. Yet you do not need complex robotics to begin. A simple pair of 10 by 50 binoculars is often the most effective tool. Binoculars offer a wide field of view that telescopes cannot match, making them the superior choice for scanning the Milky Way or viewing large open clusters like the Pleiades. They are also the ideal instrument for planetary conjunctions, framing Mars and Jupiter together in a single breathtaking view. Regardless of your hardware choice, your most important instrument remains your own biology, specifically the process of dark adaptation. The chemical rhodopsin in your retina requires time to regenerate, meaning you must spend 20 to 30 minutes away from white light to achieve true night vision. Any exposure to a phone screen or car headlight will instantly reset this biological clock, blinding you to the faint fuzz of distant comets. To preserve this state while consulting star charts, use a red light flashlight, which operates at a wavelength that does not trigger retinal bleaching. Whether you choose the raw power of an 8-inch mirror, the digital assistance of a smart telescope, or the portability of binoculars, the universe is open for inspection. The photons are arriving right now. All you need to do is look up.